Okay, so we've reached the part of the course where we're talking about energy now and how energy flows through the atmosphere system. And there's actually a number of ways that energy can be transferred from one object to another. But the two that are most relevant for our purposes, and the two that we're going to focus on, are radiation and heat. We're going to start off with radiation because that's how the process starts. Radiation comes in from the sun. And then that's going to be maybe 2 or 3 screencasts on radiation. And then we'll back up a little bit and talk about heat a little bit. And then we'll put it all together into one big picture. Okay, so radiation. So what is radiation? Well, loosely speaking, we could define radiation to be energy transmitted by electromagnetic waves. That's what radiation is, energy transmitted by electromagnetic waves. Which, of course, raises the further question, what are electromagnetic waves? Well, I think for our purposes, we can just define electromagnetic waves sort of loosely to be waves of electric and magnetic force. Electromagnetic waves are waves of electric and magnetic force. Now, you don't really have to understand this in any detail for this course, but it's something that is relevant enough to your day-to-day lives that it's probably worth going through it a little bit. So I'm going to flesh this out a little bit more, what I mean by this electric and magnetic force, and how this ends up transferring energy. So to get at this, let's suppose that we have an electron that's sitting off in the middle of the air, in the middle of the atmosphere. And incident on this electron, we have an electromagnetic wave. Now, as we've defined it, this wave is a wave of electric and magnetic force, but for the present purposes, I'm just going to focus on the electric part. The magnetic part is actually pretty similar in most ways, but it's a bit more abstract. So I'm just going to focus on the electric part. So we'll say it's a wave of electric force for the moment. And we'll say that this guy is propagating to the right. Now the electron is a charged particle. It carries a negative unit of charge. And so what's going to happen is that as this wave goes by the electron, it's going to end up exerting a force on the electron. That's actually what we mean by a wave of electric force. It's a force that's exerted on charged particles. That's what an electric force is. And what's shown in the schematic of the wave here is actually the direction that the force is going to be exerted. So for instance, at some point in time, the crest of the wave is going to be at the position of the electron. And when that happens, it's going to end up pushing the electron in a certain direction, let's say upwards. And then sometime later, the trough of the wave, the low point, is going to be over the electron. And when that happens, it ends up pushing the electron in the other direction. And so the end result is that as this wave propagates by, the electron ends up getting pushed around, first one direction, then the other direction. So we end up then with an electron that's pushed back and forth as the wave passes. You can think of this as being analogous to having a cork on the ocean. As ocean waves go by the cork's going to end up getting pushed in one direction as the crest of the wave comes by, and then falls back down in the other direction as the trough goes by. And so as these waves pass, the cork ends up bobbing up and down. It's going to be kind of the same kind of thing with this electron. As the wave goes by, it's going to end up getting pushed back and forth. So this guy is kind of analogous to a cork on the water. Now, generally speaking, we don't usually have individual electrons out in the middle of the air. I mean, it does happen, especially up in the thermosphere. There's a lot of individual charged particles up there. But more likely what you're going to have is electrons that are part of an atom. And in this case, it's kind of the same thing, just with some slight differences. And basically, if you've got electrons that are part of an atom, then what's going to happen instead is that when the wave interacts with the atom, it's going to end up pushing the electrons into different orbits around the nucleus. And in so doing, it's going to end up changing the state of the atom. So for instance, if you've got your nucleus of your atom, and then you've got electrons circling around the atom. So we've got our nucleus with our electrons. And then you've got an electromagnetic wave that's incident on that atom, propagating to the right. What's going to happen is as that wave interacts with the atom, it's going to end up pushing that electron into a different orbit. And hence it changes the state of the electron, or of the atom. So from this kind of discussion, you should probably be able to get a sense of what it is we mean when we say that radiation carries energy from place to place. Because if you think back, we had loosely defined energy as the capacity to make something happen. Well, clearly, as this electromagnetic wave propagated in and interacted with the atom, it made something happen. It changed the state of the atom. It pushed the electron into a different orbit. And so that's how it is then that radiation can transfer energy from one place to another. So just to be clear, these are electron orbits. Forgot to put that in there. Okay. But you don't actually need to understand that in a lot of detail for the purposes of this course. The main point is that radiation is a way of transferring energy from one place to another. And it's actually a little different from a lot of other ways of transferring energy in that it can happen, you can transfer energy from one object to another, in particular from the emitter of the energy to the absorber of the energy, without really having an impact on the intervening space, the space in between. In fact, you don't need anything to be in that intervening space. So for instance, in the case of the sun and the earth, where the sun is emitting the radiation and the earth is absorbing the radiation, well, in this case, there's basically nothing in between. It's empty space between them. And the radiation propagates through without really having any impact until it reaches the Earth, and then it transfers the energy to the Earth. This is different from heat, for instance. If you had a warm object and a cold object, the only way you can transfer heat from one to the other is if there's something in between to carry that heat. So you need air or water or something to carry that heat from the warm object to the cold object. Radiation's different in this way. You don't really need anything in between. You can transfer energy without really having an impact on the intervening space. Now, when we talk about the properties of radiation, it turns out that the property of these waves that has the biggest impact, or the characteristic of these waves that has the biggest impact on their physical properties, is actually their wavelength. And so that's how we end up classifying the waves as well. We classify them in terms of their wavelength, where wavelength is just defined to be, the wavelength is just defined to be the distance between the peaks in the wave. From here to here, that's going to be the wavelength. And typically we end up denoting that wavelength by the symbol down here, which is the Greek letter lambda. So the Greek letter lambda is going to denote wavelength. That's our wavelength of the wave. And when you're talking about electromagnetic radiation, it comes in all different kinds of wavelengths. The kinds of things that we're going to be interested in can range from wavelengths of meters, so from peak to peak distance in the wave is meters, down to really short wavelengths. For instance, we're going to be most interested in are what are called micrometers. Micrometers, represented by this funny symbol M in front of the M. The M represents meter, and then putting this funny symbol in front of it means micrometers. And what a micrometer is, so 1 micrometer is defined to be 1/1,000,000th of a meter. So take a meter and divide it into a million parts. Divide into 1,000 parts, and then take each of those and divide them into 1,000 parts. That's equivalent. So if you imagine doing that, taking the meter and dividing it into 1,000 parts, so that's a millimeter, and then taking a millimeter and dividing it into 1,000 parts. And you get something that's so small that we don't really have any good intuition for dealing with that because we never see things that small with our eyes. But that's actually going to be the range, the wavelengths of the radiation that we're going to be most interested in this course, 1/1,000,000th of a meter. In scientific notation, 1/1,000,000th of a meter would be 10 to the minus 6th, which means we take a 1 and then move the decimal point 6 places to the left, and that's going to give us 0.00000001 meter. So it's a very small amount of distance. Now, just for reference, this funny symbol that we put in front of the M to make micrometers, that's actually another Greek letter. It's the Greek letter mu. Mu. This is a figure that illustrates radiation of different wavelengths. Here, sort of going from longer wavelengths on the top and shorter wavelengths on the bottom. And on the longer wavelength parts of the electromagnetic spectrum, we've got things like radio waves and television waves. And then you go down to shorter wavelengths and you've got microwaves. Microwaves are down in the fractions of a centimeter. And then you've got even shorter as infrared. And then visible, the part of the spectrum that we see. And then ultraviolet. And then the really short stuff are things like X-rays and gamma rays. A couple things to note about this figure. The first is that it's nowhere close to scale. So for instance, when you're looking at the radio waves, they've got this listed as being wavelengths of 100 meters or so. And then the next one down is television, which they're listing at 1 meter. And so there should be a difference of 100 in the wavelength between the first one and the second one. Whereas in reality, as they've drawn it, it's just a difference of 2. So this is nowhere close to scale. It's really just trying to represent that these wavelengths are getting shorter as we're going down the figure through the different kinds of radiation. And again, you should keep in mind that when we get down to the part of the spectrum that we're going to be interested in, where it's micrometers, those wavelengths are so short that, it's hard to imagine exactly how short they are. The second thing about this figure is they have a column over here to illustrate the energy of the wave. And in particular, they've listed this as the energy carried per wave or per photon as they had it. And they're showing that the energy increases as we go down to the shorter and shorter and shorter wavelengths. So to illustrate what that means, I'm going to jump ahead here a slide to Let's see how to do this. There to here. And the basic idea of what they mean by that is that when radiation is produced, so in reality, when radiation is produced, these electromagnetic waves are actually produced in bursts of energy. And these bursts have a name. They're called photons. So we're typically produced in photons, little bursts called photons. You can actually think of this as being analogous to what would happen if you threw a rock into a pond. And so if you imagine you go out on some morning when the wind is calm and the pond is very flat, and then you take a big old rock and you throw it out as far as you can into the pond, what's going to happen? Well, it's going to produce waves, but it's not going to be waves everywhere in the pond. What's going to happen is that the wave is produced at the point that the rock goes in, and then it propagates away. And so you're going to end up with a wave disturbance that kind of looks something like this. So on one end of the wave, let's say that we threw the rock in over here on this side. Well, it takes a while for the waves to propagate away. So if you go far enough away from the rock, the water's going to be flat. And then as the wave propagates away, if you wait a little while, the water will come back to being flat as well. So what you end up with then is this sort of wave, this burst of waves that propagates away from the rock in a circle. Probably everybody has seen this kind of thing. Whereas in front of it and behind it, it's relatively flat. And it's that burst that we're referring to as a photon, that sort of burst of energy. Now going back to this figure, that's actually what they mean by this energy increasing as we go downward here. They're actually talking about the energy carried by each individual burst as it's produced. And there's a simple relationship that tells us how much energy is produced by each individual burst. It's always set by the wavelength, in particular by the peak-to-peak distance here. And it turns out that the energy of an individual photon, an individual burst, is just given by some constant divided by the wavelength of the waves in that little burst. And so you can see then by this relationship, as the wavelength gets shorter and shorter and shorter, the denominator is getting smaller, which means the energy carried by that individual photon goes up. So shorter waves actually carry more energy per individual photon, per individual burst of energy. So one way to look at that is that the waves get more energetic, and in some sense they get more dangerous as we go to shorter wavelengths. If we think about radio and television waves, they're such long wavelengths that the photons don't carry much energy, and we don't really have to worry about those kinds of waves causing any damage to us. You get down to microwaves, and you're carrying a bit more energy, and so you can heat up your food with them. You get down to things like ultraviolet. Well, ultraviolet, if you're exposed to that, it actually causes your skin to change color. And so it's carrying a bit more energy associated with it because it's shorter wavelength. If you get all the way down to things like X-rays, they carry quite a bit of energy per individual burst, and so they're actually capable of causing damage to your cells. And that's why you're not supposed to have too many X-rays in any given time period. There's sort of a recommended limit in the number of X-rays you should have per year. And the reason is that the X-rays, the individual photons associated with those X-rays, are carrying quite a bit of energy with them, and so they can cause damage to your biological systems. Okay, jumping ahead here. This is showing the same thing, but instead of showing the spectrum schematically like on the last figure, it's showing it with numbers over here on the right. So we've got our different types of waves or different types of radiation, and then their wavelengths over here on the right. So our TV and radio, again, we're talking meters, hundreds of meters even for the wavelengths there, so they're pretty long waves. Microwaves, you're talking fractions of a centimeter typically. Infrared, you're getting down into the micrometer range. And we mentioned before that's mainly what we're going to be interested in, is down in the micrometer, a millionth of a meter. The infrared part of the spectrum is actually a pretty broad part of the spectrum. You're talking 1 micrometer up to hundreds of micrometers. But in any case, it's units of micrometers that we're dealing with. Going down to shorter, we've got our visible. That's the part that our eyes are sensitive to. And if you look at the numbers here, it's kind of interesting that the part that our eyes see is actually a pretty narrow slice of this spectrum. It's just going from 0.4 to 0.7 micrometers. So it's a range of only about 0.3 micrometers, whereas compared to infrared, which was a range of, hundreds of micrometers. And then going down to shorter, we've got our ultraviolet and our X-rays and gamma rays and things like that. Now, the part that we're going to be most interested in is down in the micrometer part. So it's going to be sort of this part right in here. And that's the infrared part and the visible part. It's mostly what we're going to be dealing with. Now, one of the properties of radiation is that all objects continuously emit and absorb radiation all the time. So it's happening continuously. Each one of you guys is continuously emitting radiation and continuously absorbing radiation. But that being the case, or that being said, it's not true that you're emitting all wavelengths the same amount. Typically, you will emit some wavelengths more and other wavelengths less. So you'll emit some kinds of radiation more and other kinds of radiation less. And it's also true of absorption. You absorb some types of radiation better than others. So in order to characterize this, we use what are referred to as spectra, emission and absorption spectra. So for instance, in order to characterize the kinds of radiation that we emit, we use an emission spectrum. And what an emission spectrum shows is the amount of energy emitted as a function of the wavelength. The amount of energy emitted at each individual wavelength of the radiation. So for instance, down here, they're showing the emission spectrum of the sun. And on the vertical axis here, we've got the amount of energy being emitted. So the intensity of the radiation, the amount of energy being emitted. And on the horizontal axis, we've got the wavelength. So how much energy is being emitted at each individual wavelength. So the basic idea is if we go in and we pick a given wavelength, say 1 micrometer here, and then we go up to the curve and then trace it over, that's how much energy is being emitted at 1 micrometer wavelength. And in this particular case, for the sun, the maximum ends up being at about 0.5 micrometers. So the sun emits more energy at wavelengths of 0.5 micrometers than it does at any other wavelength. And then as you go to longer wavelengths, the amount of energy emitted at those wavelengths dies off. And as you go to shorter wavelengths, the amount of energy emitted at those wavelengths also falls off. So it's telling us how much energy is emitted for any given wavelength. How much energy of a given wavelength is emitted, if you like. Same thing's going to be true of absorption. So in that case, we're dealing with an absorption spectrum. And again, it's going to tell us how much we're absorbing at any given wavelength. But in the case of an absorption spectrum, it's usually expressed as a fraction or a percentage. So the basic idea is if energy is incident on you, then what percentage of that energy will you absorb? And the amount that you absorb, the fraction you absorb, will depend on the wavelength of the energy. You'll absorb some wavelengths better and other wavelengths not as well. So the figure down here is showing the absorption spectrum of carbon dioxide. And so on the vertical axis, we have fraction of percentage absorption. And on the horizontal axis, we've got the wavelength. So with ultraviolet down here on the shorter wavelengths, this part, the colored part in here is their way of representing visible. And then going to longer wavelengths, we've got infrared, and then keeping going, it would be microwave and so forth and so on. And so again, what this is saying, if we pick radiation of some given wavelength, say this particular wavelength here, then what this spectrum is showing us is how much energy is being absorbed. In this particular case, it's 100%. So carbon dioxide is really good at absorbing energy at this wavelength. By contrast, if you go off to much shorter wavelengths, say over here, then carbon dioxide isn't very good at absorbing those wavelengths. So energy at those wavelengths doesn't get absorbed. It kind of gets transferred straight through, whereas energy at these other wavelengths over here gets absorbed pretty well. And I should note that this is actually fairly common when you're looking at absorption spectra of individual molecules. They tend to have these little bands where they have good absorption, and then bands where they have not so good absorption. That actually goes back to quantum mechanics. It's actually a result of quantum mechanics. The basic idea is that in quantum mechanics, as it turns out, these molecules can only have certain energy states. They're not allowed to be in between. They can have energy state A and energy state B and nothing in between. It's kind of complicated why that is. I'm not sure anybody really understands it at a fundamental level, but that is the way it works. And so if you remember, wavelengths, at radiation of different wavelengths, the individual photons carry different amounts of energy. And so basically, these molecules can only absorb the photons that get them from state A to state B. So that's going to be a certain wavelength where the photons at that wavelength can transfer you from A to B. And then the other wavelengths, they don't work because they don't get you from state A to state B. They leave you somewhere off in no man's land, and so they don't get absorbed. So the wavelengths that end up getting absorbed are the ones that transfer you into these allowed states. It's kind of a complicated thing. You don't really have to understand that in any detail, but that's why when you look at individual molecules, they tend to have these sort of banded absorption spectra where they absorb really well at some wavelengths and then not so well at most other wavelengths. Okay, so with the next screencast, we'll come back and talk about a specific kind of radiation and a specific kind of property, specific kind of object and its properties in terms of radiation.